Welcome to Science On, science communication and networking platform. You're watching live, interactive and international science stream. My name's Oliver and I'll be your host for tonight. Tonight's all about cycles. And I'm super excited to see what have our guests prepared for us tonight. Because you can find cycles literally everywhere. In nature, on every scale, from microscopic to galactic. Also, one could argue that human development is in cycles, with civilizations rising and falling through eras. You personally observe cycles every day and night, and day and night. You get the point. You could also maybe feel sometimes that your life's just circling around in a big circle. But as many thinkers have noticed, life resembles more of a spiral. So you can find the same patterns repeating, but it's actually moving forward. And with that, I think it's time for me to finish this philosophical forward and actually to move forward to our common goal tonight. And that is to see 6 brilliant performers from all around Europe and Australia having their take on cycle. But before we do that, I would like to thank our partners. Specifically, Gymnázium Mojmirovo náměstí in Brno, Czechia, that generously allows us to film on their premises, and organizations Brno Region and South Moravia Innovation Center that helps us promote this event. And now, let me officially start Science on Cycle. This is an interactive stream, and to make it interactive, we need your help, our dear audience. We need your comments to answer questions from our guests, or to just get questions for our guests. So you can do all that in the comment sections on any platform that you are watching this stream right now. Don't hesitate to use any language. We already have technologies that can translate it to English. And also, to ask, if you ask any questions that we do not get to during the stream, at the end of the stream we will have a discussion session when we get to all your text. And just switcheroo with the cameras. And we can, there is one particular cycle that we want to reflect on during this stream. And that is the cycle of a personal development of a science communicator. Our guests, they all have their life stories and also stories as science communicators, but they are similar in one thing, and that is that they usually start at a young age with some inspirational thing or person that inspires them to just know more, that they want to explore science and scientific ways of knowing. And we will be asking all of our guests one question. And that is, can you recall the first experience you had with science that inspired you in your career or influenced you in your future career? And you can also answer this question. Please head to the comments and share your story. We would love to hear them and we will get to them during our stream. I was talking about our guests, and if you follow us on our social media, you already know who they are. But for everyone else, let me introduce tonight's guest. And first, joining us from the Netherlands is Bette. Welcome, Mark.
Hello.
Can you hear us?
Yes, I can hear you.
Perfect. So let me just ask you one introductory question, and that is, what can we expect from you tonight?
I will demonstrate the copper cycle.
Copper cycle. Perfect. Thank you very much, Mark. We will be looking forward to your performance soon. And next, joining us from Poland, it's Tomasz Ruszkowski. Hello, Tomasz.
Hello and welcome.
We can hear you. So what have you prepared for us tonight?
Well, tonight you will laugh at my face. A rubber duck will go through a window, and if you hear some in the background, just ignore it.
Thank you very much, Tomasz. See you later. And next, joining me right here in the studio is a local, David Číhal. Welcome, David.
Hello.
And what can we expect from you tonight?
You will come with me on a hypothetical cycling journey around the globe.
That sounds interesting. Thank you very much, David. We will be looking forward to your performance later. And from Switzerland, we have on stage Anja Kranjc, Horvat. Welcome, Anja. How are you doing today?
Good, thank you. It's good to be back.
Good to have you again. And what can we be excited about in your performance?
Well, as you said, there are plenty of cycles in life, and I'm going to go from, well, not so far back, but a bit back into the history to maybe something that could happen in the future.
That's mysterious. I'm looking forward to figuring out what it is. Thank you very much, Anja. See you later.
See you.
And joining us from probably still sleeping Australia is Stuart. Good morning, Stuart.
Hey, Oliver. How are you, man?
You're doing great. Thank you for joining us. And what can we expect from you? I can see already something going around behind you.
As usual, I'm going to bring more questions than answers. I'm hopefully going to get you and the visitors, the viewers' minds to kind of turn, look at some simple everyday phenomena and start puzzling, start asking questions they never thought about. So we'll be in the swing of it real soon.
Sounds great. Thank you very much, Stuart, and see you later.
See you, man.
And last but definitely not least is Adam Blahák here with us in the studio.
Hello.
So Adam, same question. What have you prepared for us tonight?
Yeah, we're gonna look on our inner cycle. We're gonna look on our circadian rhythm, and we're gonna look on some lights. It's also a good thing.
Great. So very wide variety of topics. Thank you, Adam, and we will see you later. Let me again welcome everyone who just joined us. You're watching live, interactive, international science stream. And to make it interactive, we encourage you to use comment sections on whatever platform you're watching this on. Might be YouTube, Facebook, or Twitch. All the comments we get and we can show during the performances of our guests or later when we join our discussion session. And I think that's it. And without further ado, we can officially start the performances. And for our first performance, we are virtually connecting to the Netherlands.
Yeah.
And we've connected directly to the Stellingwerf College, where we have Mark, a chemistry teacher there. Hello, Mark, again.
Hello. Nice to have seen that you can have found our school.
Yes, we did. We did. Has to look a little bit, but we did find it. And so let me just start with what I've promised, and it is to ask you if you can recall your first experience that was so formative and that you can recall right now that made you do science.
Yeah, the first time was with my father. He was also a science teacher, chemistry and physics, and he explained to me the difference between day and light and day and night and dark and light. So that was my first experience with science.
Mm-hmm. And I believe we have some visual materials that may be close to that. Did we find a good photo?
Yeah, the small boy, that's me, and the guy behind me is my father. Yes, nice picture.
Yeah, good one. Thanks for sharing that.
Yeah.
And also a next one that connects to it, and maybe cycles or is another kind of cycle. And if we could get studio to put that up.
Yeah, and that's about my daughter. She is also very fond of science, and I try to motivate her about science. And she's very enthusiastic. She has her own YouTube channel, and if you want to visit that, please do. Very nice.
Sure. Thanks for sharing that. I encourage everyone to check that out, and I wish the best of luck to your daughter. And with that, I would like to give you the stage, and we are super excited to see the first performance of tonight.
Yes, we do our best. We do our best. So first I want to start with the part of the memoirs of Ira Remsen. So yes, thank you very much. So you can read together with me. While reading a textbook of chemistry, I came upon the statement, nitric acid acts upon copper. I was getting tired of reading such absurd stuff, and I was determined to see what is meant. Copper was more or less familiar to me, for copper cents were then in use. I had seen the bottle nitric acid on the table of the doctor's office. Having nitric acid and copper, I had only to learn that what the word act upon meant. In the interest of knowledge, I was willing to sacrifice one of the few copper cents then in my possession. I put one on the table, opened the bottle of nitric acid, poured some of the liquid on the copper and prepared to make an observation. The scent changed, and it was no small change either. A green-blue liquid foamed and fumed over the scent and over the table. The air in the neighborhood of the performance became color dark red. A great color cloud arose. This was disagreeable and suffocating. How should I stop this? I tried to get rid of the mess by picking it up and throwing it out of the window. I learned another fact. Nitric acid not only acts upon copper, it acts upon fingers. The pain led to another experiment. I drew my fingers across my trousers, and another fact was discovered. Nitric acid acts upon trousers. Taking everything into consideration, that was the most impressive experiment and relative probably the most costly experiment I have ever performed. It was a revelation to me. It resulted in a desire on my part to want to learn more about that remarkable kind of reaction. Plainly, the only way to learn about it was to work in a laboratory. So, and after this, he became a chemist, and later on, he became the president of the Johns Hopkins University. So, this is the part where I will start with, because I have done the same experiment. You have seen it on the movie, and here is the result. Here is my copper nitric solution that was formed after the reaction from nitric acid and the copper coin. So this is a very nice blue colored solution, and I will add some sodium hydroxide to it. And you can see that there was a chemical reaction because we now have a dark blue solid material in it, and this material is copper hydroxide. And copper hydroxide is a non-soluble salt. And so now we have seen another reaction, and I will continue with the next reaction because we're going to heat it. So what will happen now during the heating, the copper hydroxide will decompose, and then there will be two reaction products. One will be water and the other one will be copper oxide. And copper oxide is a blue chemical, so you can probably see a small difference in color already. It's very small. This takes a while. So now the color is changing. And color change is one of the things that is necessary to have a chemical reaction. It's one of the things that will happen. Okay. Yes, it starts working now. Not very, yes, there it goes. So you can see there is a black material now, and that black material that is copper oxide. It's not as many as I have expected, because when I tried it earlier today, I had really a very black material in it. So, okay. So normally during the copper cycle experiments, they now add sulfuric acid to this, and then the reaction of the copper oxide will take place, and then copper sulfate will be formed. But I want to have a very special final, so I'm going to use hydrochloric acid. And the question for the audience is, what color does the solution get after adding hydrochloric acid? I hope red. That would be nice. Yeah, the color of love. I hope red. Yeah. Green. Niet veel hoor. Echt, ja, is goed. Green, C. Okay. Now let's find out. So I'm going to add hydrochloric acid to it. Een beetje flauw moeten we misschien. Oké. Okay. It should turn blue. I'm going to change because I prepared. So the solution that the color of the solution is blue, a little bit green, because the product we have made now is copper chloride. So in this solution we have now copper chloride and hydrochloric acid, and I will add some more hydrochloric acid because I need an excess of acid. So I want my copper back, and hopefully I will get my copper back after this experiment, and I will use aluminium foil for this. So the aluminium will react with the copper chloride and change with copper, and then the reaction product will be aluminium chloride, and the aluminium will react with the hydrochloric acid by forming hydrogen, and hydrogen is a gas that can burn, and because of the excess of copper, hopefully the color will be nice. So we will shut the lights a little bit down. And then the aluminium goes in. You can see there's also a small reaction. You can see some gas. You can also see a brown material that's in the Erlenmeyer beaker. And you probably can hear the noise of the hydrogen gas. You can see that the foil is moving. And now I want to collect some hydrogen gas. En moet je de camera misschien weer ietsje naar achteren doen, ik ga het er weer zo aansteken. So, and now I try to light it. So now you can see nice flames with a blue color, and the blue color is caused by the copper. Let's try again. It looks a little bit like the northern light. So now I will let the aluminium react more with to end this reaction. So you can see there are a lot of changes now in this material, because the fluid was blue, really blue, and now there's just a little bit blue-green in it. The aluminium foil was silver color, and you can see the material here is brown, and the brown material is copper. So, Sarina, can you show the PowerPoint? So the reaction that took place, you can see now on the slides, but that's for when you are at home, you can look it back. But I want the next slide, please, because you saw a circle. Forward slide. Okay. Sorry. You can. Thanks. We started with copper. Then we created copper nitrate. After the copper nitrate, we created copper hydroxide. After the copper hydroxide, this reacted to copper oxide and then to copper chloride, and then we came back with copper. So I think this is a nice example of a cycle. And this was my experiment for today.
Thank you, Mark, very much for your experiments and also for sharing the story of Ira Remze, and interesting answer to the question of the experience that inspired him. And also I have to admire all the chemical experiments when the colors are changing, and when you added the little pops to it, so mini explosions, that was really lovely. And I believe we have a question from our audience.
Oh, nice.
Okay, so the question is, what about the vapors in the reactions? Is it safe? So what gases were produced and are they safe?
The first experiment is very dangerous. So that's the reason why I did film it, and I did the experiment in a fume hood. So I didn't want to do that in a classroom because it's dangerous. The other experiments are safe to do. You can do this in a classroom. It's no problem.
Mm-hmm. Thank you. And also I have a question for you. So when you showed us at least a part of experiments called the copper cycle, but when you Google copper cycle, as I did, you get a different kind of cycle on a different scale. On an environmental scale, as a copper cycle, similarly to a water cycle, for example, is an exchange of copper in the environment from hydrosphere to atmosphere to lithosphere and so on. And I wanted to ask you, is there a good link in between these two scales? So for example, in one reservoir in the environment, the copper is in one stage, and in the other, it's in another. Can you find a good link in between these two kind of cycles?
Ooh, that's a very difficult question. I think it's good to know that when you have copper mixed with chloride, or copper mixed with sulfate, or copper mixed with whatever, you can break the bonding and create your elemental copper again. So in sense of recycling material, this could be very interesting.
Okay, thank you very much, Mark. And we can definitely follow up. If you have any more questions for Mark, don't hesitate to ask them, and we will get to them in our discussion session. And with some comments from our audience, we will go to another experiment.
Thanks.
Thank you, Mark. And moving on to our next guest, I welcome Tomasz back. Welcome back, Tomasz. We didn't want to reveal your exact location as it is your home, and honestly, we couldn't find it on our side. So
you didn't ask, but I was waiting. I was really watching the map, zooming in. I was like, okay, where will they land? But we snap above the wall, so
yeah, some privacy laws in EU,
which is quite close to the place I am now.
Okay, perfect. At least we got close. And so, as I promised, I will ask the same question all of our guests. So, Tomasz, can you recall your first experience that influenced you as a science communicator in the future?
Well, in my memory, I didn't go that far back as Mark did, because the first memory I did recall is from high school, so not that long ago. And it was when during the biology lesson, I think, we were talking about the nervous system. That's me. That's the high school me. And I will go back to the story, but if you show the picture, because I have a prop, and if you go with the picture a little bit lower, you will see that I still have this T-shirt. It's the same one. It's the same one. Because for men, we don't throw our clothes if they are still good. So this one is over 20 years old, and it's looking still good. The colors are the same. Back to the story. The biology lesson and the nervous system, and maybe even at the same day, the history lesson when we were talking about the Stone Age, the people trying to use tools for the first time. And it hit me that caveman, let's call him, was trying to use a rock, for example, or trying to figure out how to use a fire. And at the same time, his own body was using electricity to send information at very high speed, something that caveman and his relays will have to wait centuries to go to figure that out. And that was like, whoa, that's cool. So that's my memory.
Yeah, thank you very much for sharing. And as you mentioned, high school, schools are usually like answer to these types of questions. And I don't want to get too political here, but in Central Europe, let's say 20 years ago or 30 years ago, we struggled with the transition from Soviet era to post-Soviet era of education. And I would like to ask you, what was your experience with your institutional education on your elementary school, and then let's say also secondary school regarding to science education?
Well, in Poland, the things are changing in a few years. Like I remember at least 3 changes in the way that the schools work here. So it is You said that we were in a transition. I think we are in one continuous transition from one system to another. So things are changing, but probably still the way I work as a science communicator is something that schools in Poland are still trying to use themselves, but it's not like everyday science. It's not presented the way I would like to see it in schools, in high schools and stuff like that. So maybe in the future, maybe my kids, maybe my grandkids, or so on, so on.
Yeah. As you mentioned, a continuous cycle of improvements, right? And hopefully it does continue to get better and better. And so, yep, thanks for the quick introduction. And I will now give stage to you. And I'm looking forward to see you doing your experiments.
So thinking about the cycle, I came with things going round. So I have some equipment that is spinning in one or another way. So we basically go into optical illusions today, which somehow contributed to the stream I already did with you guys about the evolution of the eye. And I will start with something like that. Probably all of us know if they are right-handed or left-handed. Some of us probably know if they are left-footed or right-footed. But what about our eyes? Do we more often use our right eye or our left eye? Because they are constantly, but because they are constantly both open at the same time. But it appears that for our brain, the image from one eye is a little bit more important than the image from the other eye. And it is called ocular dominance. I need to, my eyes switched to the notes, because in Polish it is a dominant eye, and in English it doesn't translate like that, and I didn't want to make a mistake. So, ocular dominance in English. And you can test your eyes to see which one of your eyes is the dominant one. And when I do this experiment, for example, at school with kids, I, of course, use a rubber duck. A rubber duck in a helmet, because it's going to sit above my head, and sometimes it falls, and I don't want it to hurt itself. So what you are going to do, you are going to look at the rubber duck on my head. You can go a little bit back from your computer so that you have enough space to use your thumb as well. So the way it goes, you look at the duck on my head with both of your eyes open. You can blink, of course, but don't look anywhere around. See? That's what the helmet is for. So eyes open, you're looking on the duck, and with both eyes open, you straighten your, let's say, right hand with your right thumb up, and you put that thumb on the duck. And I know that your thumb will appear transparent, stuff like that. Don't worry. Put the thumb on the rubber duck as good as you think it is. And now, without moving your hand or your head or your eyes, close one of your eyes, the left one and then the right one, the left one and the right one, left, right. And you will see that at what point the thumb will be on the duck. And with the other eye closed, it will move to the left or to the right. For me, as a person with the right eye dominance, when I close my left eye, the thumb is where I want it to be at the beginning. And when I close my right eye, my dominant one, the thumb switches to the left side. So for me, for my brain, the image from the right eye is a little bit more important than the one from the left one. Some of you maybe have the left eye dominance with the right hand or the left hand. It's really, there isn't any connections with one thing or another. And here goes my question to the audience. What for we need 2 eyes. Not 1, not 3, but 2. Because if one of them is dominant, if the brain prefers the image from one of those eyes, why do we need 2 of them? Think about it, and I will change a prop for this little, I think, nice optical illusion. And your task is going to look on this spiral as it goes around, and I would like you to force your brain to see a tunnel. Like this flat disk is not flat anymore, but you can throw something inside of it. For example, let's say a rubber duck that goes inside this tunnel, this hole. But with this optical illusion, you can also force your brain to see something that is not hollow, but is pointing towards you, so that this little one is not far away, but close to you, like you are watching a hill or something like that. Some of you may even switch from one eye to another, or from one view to another, see a hollow or a hill, something pointing out to you. Normally, when I present this to kids, I ask them to close one of their eyes. And now we can go back to the question, why do we need 2 eyes? Okay, we have an answer that's for the deep perception, so to better perceive the distance. And of course, that's right. That's the correct answer. The other one is that you see more things on the left side and on the right side with 2 eyes, but with 2 of them, you can see the world in 3 dimensions. You know that something is far from you or close to you, because your brain is connected to those 2 images from your left eye and from your right eye, and it connects them, giving you one picture of the world. And depending on what the difference in these 2 pictures, your brain tells you if something is far away or close to you. So that's why you need 2 eyes to see world in 3 dimensions. And going back to the spiral, I said that normally I ask people to close one of their eyes when they're looking at this, because with most of the optical illusions, it is better, it is more easier for us to get to see the illusion itself when we don't see the world in 3 dimensions, if we don't use both of our eyes. But in a stream like this, the situation is a little bit different. I didn't need to ask you to close one of your eyes, and still you probably get the illusion. It is because you are watching this illusion not only through your eyes, but also through the lens of my camera. And the camera is making the image flat for you. Your eyes can see the difference between left and right. They can't give you this depth precisely as good as you would see it here live in Warsaw, in my room. So most of the optical illusions in life will work better if you close one of your eyes. Try it on your own when you see an optical illusion next time. But if you are watching it on a TV, on your computer, on your smartphone, stuff like that, you can use both of your eyes, because the camera itself will flatten the image for you. In the introduction to the stream, I said that I will give you the chance to laugh at my plays. And to do that, we need to change the spiral for the one that looks like this. And this illusion is quite different from the others, because even in live situation, you can use both of your eyes, and it will still work as good as you will use only one of your eyes. Now, what you are going to do, you are going to stir in the middle of the spinning spiral. And by saying you will stir in it, really stir in the middle of the spiral. Don't look anywhere around, because the spiral itself is not the illusion we're looking for. It is only preparing your eyes for the illusion. So the better it works if you look directly in the middle as long as you can. And I know that after a few seconds, your eyes will really like to look around, look in different directions, because they don't like to look in such an image like this. But keep staring. Force yourself to look in the middle of the spiral, because the spiral is preparing you for the illusion we're looking for. The task of the spiral now is to make your retina tired. Retina is the part of the eye that is light sensitive, and now it's getting the sensation of black and white, and the movement, and it's getting tired. And in a few seconds, I will take the spiral away, and in the same place the spiral is now, I will put my face. And I will ask you to stare at my nose. And that's the moment when you will see the actual illusion. Okay? Keep staring at the spiral, and now stare at my nose. And now you see the illusion we are looking for. My head is probably spinning or getting bigger or smaller. It is maybe even shining and stuff like that. The thing you are experiencing now is called the after image. It is the image you see after you saw the image. After images occur to you mostly when you look at something bright. For example, on the sun, on the light, or something like that, and you get a lot of light going to your eyes. And then you have this irritating spots everywhere you look, in the place when your retina got that huge amount of the light. Here, with the spiral, the after image was produced by the movement of the spiral and the contrast of white and black, white and black. And if you are still seeing my head going bigger, small, don't worry, it will disappear in a few hours, days, or weeks, or something like that. Now we're going to the point that optical illusions very often use movement to fool you. They don't like your stereoscopic side, and they very often also use contrast, like black and white stuff, and they also very often use perspective. Perspective we use over here to see the hill or the hollow in the disc. But now I would like to show you the very favorite optical illusion of mine, which is called the Ames window. And it looks like this. So it is a window, basically, and it's called Ames window because it was invented by a guy called Albert Ames Jr. Junior? Well, you know what I mean. An American scientist. So it is a window. It is a window that is made to appear in the perspective. So this side is, you can think that it is far from you, and that this side on the other end is close to you. But in fact, they are both the same way. The window I'm holding is not rectangular, but it is more trapezoid in a shape. But for your brain, this side is farther and this side is closer. If I rotate it, obviously the sides switch places. If I go like this, it is like you are looking from the ground up for a building, for example. And if I go like this, it is like you are staring from top to the down. What's more, we also have these black shadows over here that are giving some 3 dimensions to this object. It appears thicker than it actually is. And all of that makes the Hermes window a very special thing. But to see the actual illusion, we need to spin the window. And you are going to start somewhere in the middle of it. Just let me attach it to the drill. And also, for better experience, we will change the wall. Oh, the side of my room. Whoop. Cables everywhere. You don't see me. And now you see me. And you see the Hermes window. Somewhere over here. Great. So what I want you to do is to look somewhere over here of the rotating Hermes window. And after a few spins, you should get this sensation that the window is changing the direction it is rotating. You should see that it goes to the left, and then suddenly it starts going to the right, and then to the left again, and to the right again. But the truth is that the drill is spinning the same direction all the time. But you don't see the window going the same direction at the same time. It goes to the left and then to the right. It changes the direction. And it's, of course, because of the perspective, because of the shape of it, and because of your brain that is thinking that this is actually a window, and the windows are most of the time rectangular, not triangle, not trapezoids. So when the window is going to the side or the other side, your brain doesn't know which way it is spinning, because both of the directions are as possible as the second one. And for me, this is quite crazy thing to see that the Hermes window is switching the sides, it is rotating. But we can go a little bit farther with this experiment, adding a rubber duck, because why not? And even 2 rubber ducks. We will put them in the middle of the window, just like that. Go back to the wall. Oh, no, a little bit. Okay. So we have 2 ducks going across the window. And now, all you have to do is look at the window the same way you did a few seconds ago. And now, we'll get a new sensation. The window itself is changing the direction. It goes right, then it goes to the left, it goes to the right, it goes to the left. But the ducks, they are going through the window. They don't have this perspective. Your brain knows which way they are rotating, but at the same time, your brain doesn't know which way the window is rotating. And the connection of those 2 visions gives you the weird sensations that the ducks are going through the window the way they shouldn't do it. Okay, back to the place over here. All right, thank you thank you that you wanted to watch this, and I hope you appreciate it. And now back to the studio. Oliver.
Thank you. So sorry for cutting you off a little bit.
No, I think you only cut your own name, so it's on you, Horvat.
Yeah, everyone knows by now. Okay, so thanks for your experiments with the optical illusions, and I have to say, like, Ames window was one of my favorite optical illusions already, but using the ducks, it elevated it to the whole another level. So thank you for that. And also, I have to say, it's quite fitting that trapezoids have a word trap in them, because it's a trap for your perception. So yeah, it's a good coincidence. And I believe we have a question for you from our audience.
Yes.
Okay, so I already mentioned Ames illusion was one of my favorites. And what about yours?
Definitely, the Ames illusion is also the one I really like, because it works really, really good also in live situation, not only in videos, but looking around, there's also one thing over here, which is also a very nice illusion. It is a dragon that is going with his eyes. It's looking after you. Yes, I'm moving it, I'm rotating it, and his eyes are staring at you all the time. But if I go around, you would think happens that there's a weird shape. But I think Ames window is my favorite.
What I like about these kind of optical illusions is that even if you know how they work, they still trick you. You can't do anything about it. And I believe we have another one. Okay, so Tomek, will you have any other public science performances in English this year? Please, when and where? So someone wants to see you live.
I hopefully going to Slovenia this year to Znanstival, a great place, a fabulous festival with a lot of presenters with all around the world. And so often a very nice weather there in Ljubljana, and it starts at the first weekend of June, I think. I need to open the calendar and see. It starts at the last Friday of May and the first weekend of June. So if you have time, go to Slovenia, to Ljubljana, see the Znanstival and enjoy all the things you can see there and all the performers.
Thank you for the invitation, and I think we will get to more tips for everyone who is enthusiastic about learning more about science and science communication during the discussion session. So keep connected, and thank you, Tomek, for your performance. It was really beautiful. I loved it, and I'm looking forward to seeing you soon in the discussion session.
Thank you.
So these were our first performances, and for everyone joining us just now, you are watching live interactive international science stream Science On Cycle. I would also like to remind everyone that tonight's theme is cycle, and we encourage everyone to share their stories. What were their first experience with science that they found that was memorable and maybe influence them in how they choose their future path. And I believe we have one inspiration already. And that was a rainbow, which is a beautiful natural phenomenon that just makes you to want more and discover more how this happens. So keep them coming. We want to see more of them, and we will get to them later. And now we are not actually connecting anywhere else in Europe. We have our next guest here with us. And I'm joined by David. Welcome, David. And as usual already, I would like to ask you if you can recall your first experience with science that inspired you, that was memorable, or that excited you to follow paths of scientific exploration.
Yes, I will repeat after Tomek that it was not that long ago. It was when I was at high school. I had this great chemistry teacher, Pavel Zohar, who taught us biochemistry at this particular lesson. And I was so amazed by all the cycles going in the human organisms or living organisms that it inspired me to pursue my studies, and so I went to college to study biochemistry myself.
Thank you, David. So another shout out to a science teacher in high school. So you can see that you all have an impact on your students, and you can give us such great performers as David and science enthusiasts. And David, you are now pursuing a career of a biotechnology engineer. Is that correct?
Yes, it's correct.
And you are still doing some science communication. And I would like to ask you, what are your ways to still stay, let's say, in the loop of science communication and science popularization? What kind of science content do you consume?
Most of the time I'm consuming these large YouTube channels with I don't know, Mark Rober or Smarter Every Day and stuff like that, to be in touch with the science. But time to time I like to join this stream and these wonderful people to get really into stuff.
Thank you very much for all the tips. And to everyone who wants to get to more science content, you can definitely watch these YouTubers that David mentioned, but also our YouTube channel, where you will see short videos from this stream as well. So, and now, David, I can physically give the stage to you.
Yeah, thank you.
And best of luck. And I'm looking forward to your performance.
Okay, so I was talking about cycling or going around the globe, but I will do it a little bit differently. Imagine that you would take a rope and you would tie it tightly around the globe. And now you would like it to be 15 centimeters above the surface, above the ground. How much longer should the rope be to be 15 centimeters above the surface? Our Earth has a radius of 6,378 kilometers, which make it around 40,000 kilometers circumference around the globe. So you have this huge, long rope, which is 40,000 kilometers in length. And how much more do you need for it to be 15 centimeters above the ground, all the way around the globe? So write your guesses, and I hope they'll be close to this or far. And don't mind how the rope will stick to the position. It will just stay there. It's like magical rope, which can stay in a particular height, so it doesn't mind.
So do we have any answers yet? No one. Okay, if you're shy, you can even write if it will be like in kilometers, hundreds of kilometers, thousands of kilometers, or meters, centimeters. It depends on you. So any guess is a good guess here. Very much. Okay, so this is also a good guess. Circumference of the Earth times 2, which would make it like 80,000 kilometers worth of rope. Okay, that's a good guess. It could maybe make it to 15 centimeters. 1 meter, Adam says. He could be close, who knows? 1 feet or so. Okay, 1 feet is around like 30 centimeters. 56 centimeters. Okay, that's close too. Well, let's take a look at it. I can't show you a rope which could have like 40,000 kilometers. I'm not that rich, so I will just pretend that this bottle has a circumference of the Earth. Okay, it just has some circumference. I don't care what the exact number is. Only thing that I care about is to measure it. So I have a rope here, and I can show you that this flask. Oh, where the hell? Wait a second. Wrong rope. Wrong rope. Sorry. This rope is the correct one. Okay, so if I tie this rope around the bottle, you can see that I have a mark here. This mark represents the length of the circumference of this bottle. If I add 1 meter, okay, 1 meter of rope, and I will do my best to put it around this bottle so it will make a circle around it. You can see that the circumference of the rope circle now is bigger than the flask. But how much bigger is it? I have a handy tool here, and I can measure it. Okay, so I will measure it from 4 sides, and we will get the average of it. So from here I have like 14-ish, here's 16-ish, again 16-ish, and 14, which makes it twice 14, twice 16. It's around 15 centimeters bigger radius than the radius of the flask. Okay, now you can say I answered my question, but still the flask is a little bit too small for a globe, for an Earth. Okay, I will take bigger thing here. I have a clock. Okay, here's a little clock. And I can again measure its circumference using pre-measured rope. So I will again tie this rope around. You can see that I have a mark here, which makes it, this is the circumference of the clock. And here, again, I have a meter of rope. And again, I will place it around the clock, so it has the same distance from the clock all around. I'll do my best. It won't be perfect circle. I'm not that good yet. But I think this is good enough. And again, I will use my handy-dandy tool and measure 4 sides. Okay, so it's 14, 13 and a half, 14, and 14. Okay, so now it's about 14 centimeters. But you could say again, clock, still too small. Okay, I have a bigger circle here. I have a hula hoop. And the hula hoop has a circumference of 2.5 meters. It's just like pretty bigger than the bottle. And again, I have here a rope which I extended by 1 meter. And because this would be like too hard for me to make a really good impression of a circle, I have prepared a different type of circle. I have here a wired circle, and I will place the hula hoop in the center of it. The circle, the steel circle, has the same length or circumference is the same as the length of the rope, which is the hula hoop plus 1 meter. Okay, and I will measure it again, so you can see. So here it is 15, 16, 16, and 15 again. So it makes it around 15.5 centimeters. So again, I'm pretty close. And as you can see, I only edit, every time, I only edit 1 meter length of rope. And if you're good at math, you can divide that meter by 15 centimeters. And you will get something around 6.28. And 6.28 is 2 times pi. And if you remember from math class, from high school possibly, or maybe elementary school, the equation to calculate the circumference of the circle, you will get 2 pi times radius. And 2 pi is the coefficient which, if you get the bigger radius or the amount or which you enlarge the radius, you can make it that larger by the 2 pi. And that it's still the same. You could see that it's 15 centimeters all around. It's hard to imagine it that it would work around the globe. But think of it this way. If you had not circular shape, but rectangular shape, like this rectangular, imagine this green rectangle the size of the Earth. And you would like to fit a bigger rectangular shape around a square, around that previous big square, which would be only 15 centimeters above the edges of the previous rectangular. You would add 15 centimeters in every side, which would get you to 1, 2, 3, 4, 5, 6, 7, 8 times the 15 centimeters, which is pretty close to those 6.28 with the circular shapes. So that's how you know. If you would like to get a rope which would be 15 centimeters above the surface of the Earth, you would need the exact circumference of the Earth plus only 1 meter.
Thank you, David. Thank you, David, for showing us this really unintuitive fact when you think about it. But when you look at the formulas, it does make sense. And what I wanted to ask you is that would it also work the same way for area? For example, if you did not have a rope, but you had a sheet, a giant sheet that you would get all around the globe, and you just wanted to have it 15 centimeters above the globe, would this giant sheet, would it matter if it was a globe or if it was just a small ball?
I think that the equation there uses like square or the free root of the radius. So I don't think it would work this way. It wouldn't be like this small amount. So I don't know. I'm not sure, but I don't think it would work like this with the surface. Yeah, because it's like the third dimension.
Mm. Yeah, it makes sense because pi times r squared, right?
Yes.
Yeah, so it might grow faster than just the circumference. And do we have any question from from our audience? I believe so. And what about the fact that the Earth does not have a flat surface, like a clock or a bottle or a hula hoop that you used, but there are all the mountain ranges and valleys, so what about that?
We would just pretend that our Earth is a perfect ball. If you were paying attention enough, you would see that even the hula hoop wasn't a perfect circle. So it's just a math problem, and as you know from school, math is always ideal.
Yeah. I think it's also a lot of times in physics that a lot of things are just like perfect spheres.
Yeah.
Let's pretend it's perfect sphere and what it would behave like. And so yeah, thank you very much, David, and I will see you in the discussion session. And now it's Switzerland calling. Welcome back, Anja.
Hello.
So you're joining us from CERN in
Yes.
Switzerland. And when we are talking about cycles, I cannot just not mention the biggest, let's call it, elephant in the room. And it's just the Large Hadron Collider that's in CERN. It's just the largest man-made, let's say, physical cycle that I can think of. So I wanted to ask you, how close did you actually get to the actual structure of the LHC?
This close, I would say. So I was in the tunnel several times, and I've been to see the experiments and everything. So yes, I've gone 100 meters underground to see the biggest man-made machine.
Perfect. A little bit envious. I would really love to see it on myself. But yeah, and I would also like to actually ask the promised question, and that is, what was your first experiment that you can recall that inspired you to do science?
Well, my trip to science wasn't straightforward, but I have to go with the same thing as most of the people before me said. So I was inspired by a teacher. So it wasn't one experiment or one experience. It was a teacher that inspired me to go into physics, despite me, until I was like 16, being absolutely certain I'm not going to go into STEM. I'm not going to go into natural sciences. I was a hardcore social scientist beforehand.
Yeah, I think we have some visual materials, not supporting that, but at least from that time. Is that correct?
Yeah, that was still the time when I hated physics. I remember when I was like super young, I was really excited about looking at National Geographic, and especially this show called Storm Chasers, where people would be, running after tornadoes and stuff. And I remember talking to my mum and being like, I really want to be a storm chaser when I grow up. And she just told me, well, you just need to go study physics and you can do that. And I was like, oh no, no, that's something I won't do. And here I am at CERN.
Well, that's an interesting story. Thank you for sharing. And now, nothing left for me to do, just to give the stage to you, and we'll see what have you prepared for us.
Fantastic. Okay. So, yes, as mentioned before, I am at CERN, and CERN is very known for it's not the biggest cycle, because I ISS has a bigger cycle around the world, but we are very close to that. So it is the place where we have the Large Hadron Collider. That is a 27-kilometer ring. And in that ring, we are accelerating protons to almost the speed of light. But the thing is, we can't accelerate protons all the time. That would have been a waste of all our resources. But we can, however, make them go in a circle by not touching them. So in order for me to show you how that is done, as I said before, I need to go a bit back into the past. And some of you might already be able to know that. I have here one very specific machine. You might remember it. If you remember it, just to let you know, you are probably relatively old. This is a cathode ray tube TV, and it was, well, basically, it was a particle accelerator. So it was a particle accelerator, and you can see that, on the other side, because my technical team, they were able to open this up, and what you can see here in the back, these are all, wires and everything, and it is a cathode ray tube. But this red thing over here, this is not something, moving my hand and my camera, bad idea. So this red thing here, that's not something you typically have in a TV. Of course, this is something that we installed, and that is a very, very tiny magnet. And now, let's see what that magnet can do. So I'm going to turn on my TV. At one point, it's going to show an image. So you can see the image, and you can also see, if you are younger than me, you can now see why your parents loved going to the cinema, because the image quality is not the best. But with a knob that I have over here, I can turn that magnet inside and out. And let's see what happens on the screen. What you can see is that when I put the magnet in, what you can see is that the whole image gets distorted, and we have a lot of tiny little rainbows and things like that. And this is one joke I love doing with this TV, and that's if I use a different magnet and make it go closer from the front, well, this is the only black hole that we can create at CERN. So nothing else can we create with the LHC, but this one here is, of course, something we can do. And this black hole, of course, is not completely black, but why is it there? Well, it's because magnets like the one I have in my hand, they are actually changing the direction of the path of charged particles. In the case of this TV, it is electrons, and electrons are negatively charged particles. And of course, these negatively charged particles travel typically in a straight line, but if we put them in a magnetic field, they would like to go, well, in a cycle, or at least in a circle. So this is the first thing that I can show you with a cathode ray tube, but now let's see it just a bit more scientifically, not so much with not my grandma's TV, but, well, the TV I used to have when I was young. Probably that was the TV that I used when I was watching those storm chasers. So what I have here is basically our setup for a cathode ray tube. This is how a cathode ray tube looks like. So you have a tube, and here we have a heating part that heats up our electrons and just accelerates them towards the front part. Of course, for that we need some electricity. So I will now put in some voltage, increase the heating, and then create a little traveling line. Of course, I I can also just make a dot. So we have a dot over here. This dot is when an electron interacts with the screen in front. It's the same thing as was happening on the TV before. But what we can also do is, if I change it to here, and also I use an electromagnet that I have here as well, what we can create is we can create art. So depending on where I have this magnet, you can see the shapes changing. That is because these electrons are trying to go in, well, in a circle, but we cut them off just slightly too fast. Okay. And now before I go to my final experiment, I have one question. So my question is, and you can put it on the screen as well, my question is, where is the biggest magnet in the world? We have 4 options. We have China, Switzerland, France, and USA. And of course, I already talked about the biggest man-made machine in the world that is located here in Switzerland at CERN, called the Large Hadron Collider. But let's just see, what do you think? Where is the biggest magnet? Of course, this magnet is going to be an electromagnet. Oh, we have the first answer already. USA would make sense. Yeah, they like having big cars and big machines. And I absolutely love how all of these answers are coming out. Actually, I forgot to specify one tiny little thing. I didn't say that that magnet has to be working already. If you don't count working magnets, if you don't only count working magnets, then the biggest one is to be in France, in a research facility called ITER, where they're trying to create, well, really cool experiments. And in that one, they have a magnet, a toroid magnet, that is several thousand tons heavy, and several meters in diameter, and it is used to sustain really, really, really hot plasma. And I mentioned toroid, and also when my picture went out before this stream, everyone was talking about toroid plasma. And of course, for that, I need to show you a toroid plasma. That is going to be done with a bit different experiment, and it's an experiment that took me a whole day to actually make it work, even though I wanted to make it work for ages already. So let me change my camera once more. So here I have a setup of high voltage equipment. So we have a transformer, we have a rheostat, we have some other stuff, and we have a nice little ball over here. And let me see if I can make my camera, yes, show it a bit more steadily. So this ball over here, it's filled with a mixture of 2 gases, of xenon and neon. And around it we have 4 loops of copper wire. And what we have here in the back, I don't want to show it because it's kind of dangerous, is a spark gap. So we're going to create, or I'm going to create, sparks that are going to be jumping and sending some electric signal. And let's see if we, in this ball, can create a toroid, so a donut-shaped plasma. Okay. As I said, it took me the whole day to make this work, but sometimes it just doesn't work with me on the first try. So give me a second. This is always what happens with my experiments. They always need a second try. And this. Okay, so now we can actually see it. Every time we have a spark, we get a toroid plasma. That is because the electric field in here is the highest on the sides, just next to that circle. And it creates the fourth and the most common state of matter, namely plasma, for just that tiny little second. And I find that absolutely amazing. It's not the plasma that we will have at ITER, but it's pretty cool nonetheless. I hope you agree with me. And that would be it for my side.
Thank you, Anja, for an electric performance. And I would like to ask you, who did the circuitry for the toroid plasma machine?
Sorry, I couldn't hear you. There was a cycling of noise.
Yeah, I was just asking who did the circuitry for the toroid plasma machine. So was it you and your team, or did you just?
That was simple. It was me.
Yeah,
that's why I didn't work the first time around.
It just took a lot of time fiddling with it, right?
Oh yes, absolutely.
Okay. Perfect. And do we have a question from audience? And if not, I encourage everyone to ask about anything you've seen already. We've seen 4 performances. There are still 2 to go. And we will definitely see Anja again during our discussion session when we also get to your questions and comments. So thank you, Anja, again, and see you later.
See you.
And now we will travel the most distance all around the globe, or at least like half of the globe, to Australia. Welcome back, Stuart.
Good evening there, Oliver.
I see that it's still going. Was it still on while you were watching other performers?
Everything has its own cycle, so it was cycling while we were watching the other performance.
Yeah. Okay then. And talking about cycles, I promised one question, and you will not be the exception. So I want to ask you: do you remember or recall like the first experience with science that inspired you to do and pursue science education in your career?
Look, I would probably flip my answer compared to some of the others, and I can't remember a time I wasn't interested in science. I really can't. And so I grew up in the country, and I was always taking things apart, always making things, always full of questions. How do things work? Why does it work? And so I had a passion to kind of find things out. And when I kind of eventually got to school, sort of teachers and science teachers were kind of the people I went to go and ask questions. And that kind of set up a relationship that I had with kind of science teachers and school as, you know, a place that kind of helped me give me answers. And that's really what I've spent my life looking for good questions, and that's what we'll do tonight.
Mm-hmm. Yeah, and we have a visual material by you sent to us. And can you tell us a little bit how this photo fits into the cycle you just mentioned?
Mentioned there. So that was for most of my professional life. I've worked with Australia's hands-on science centre, Questacon, and I in fact started working with the founding director of Questacon over 40 years ago, when that shortly before that photograph was taken. And so we were building and developing and learning how to make interactive exhibits, how to do science shows like the things we're doing tonight. And one of the visitors we had there was Ben and Charles, and that was me explaining polarizing light to Prince Charles before I gave him an activity that we weren't meant to do, with fingers in his ears and banging his head. There were a lot of that's a story for another time.
Okay, thank you very much for sharing that with us. And maybe we wanted to ask you, have one technical ask.
Sure.
It's a little bit. We have a little bit trouble of hearing you clearly. It might be from the noise, background noise of the bottle circling around. So it's just a heads up for you that it will be better for the performance.
I'll make sure I project if that's going to help.
Or just shout so you overshout the background noise. It's up to you how you deal with that. And okay, so now the stage is yours, and we are super excited to have you with us today.
Thanks, Oliver. So for this evening's, or here in Australia, the very early morning, it's just coming up to 5 o'clock. I thought I would revisit some of the activities which we've shared on Science On, both myself and Chris and Diane. I've kind of looked at this property of resonance and pendulums before. You can see one in the background. We're all kind of familiar with, I think we're fairly familiar with a basic pendulum and the properties of a pendulum. It's kind of the essence of regularity, of predictability. So one of the things which I'm always looking for is when I see something and I think I understand it, coming back and asking more questions. Do I really understand it? Can I explain everything? What else do I see going on? And so follow me this evening as we go on a bit of a journey, looking at some of the things which might seem familiar. And I'm going to share some questions which, to be honest, I've got some questions I don't have answers to. And they're the ones I love because they provoke thinking. I love thinking. If I just give you an answer, you'll stop thinking. So I'm going to give you questions tonight. So behind me, we have a pendulum. You probably can't see it on the camera shot that you've got at the moment, but at the very top of the pendulum, I've got a small little motor that's going back and forwards, and it's pulling the pendulum along, and we can see that the pendulum is swinging. And so we're doing this to the pendulum. And now, all I'm going to do, so it's a driven pendulum, we're driving it along. So I'm just going to literally just change the speed of that motor just by 1 millisecond, just by a millisecond. Which way should we go? We'll go up a few. And we'll see what happens just after a moment or two. So it's now just going just a little bit slower, about 2 milliseconds different than before. It looks as if it's still swinging, and we have faith. And we'll see just with that little change, the amplitude of the swing has died down. And now, in fact, even though we're still pulling the string, the bottle's not going anywhere. It's now perfectly stationary, or nearly so. So this is one of the things which helps us understand this kind of topic, which we've covered before here on Science On, of what we call coupled pendulums. That's one pendulum working by itself. What we'll do now is we'll go over to my workbench and we're going to look at two pendulums sharing the same string. Let me just change a camera here. See if I get it right. Those are the two pendulums. We'll have a look down on top. So we're now looking down. All right, so this is the direction of gravity. Here are the two pendulums that you saw. And what we normally do, the standard kind of demonstration that we do, is I will pull one back and let it go. And then all of a sudden, almost as if by science, because there's no magic, one of the pendulums will stop, the energy will be moved over to the other one, and then it'll come back. And then there'll be a transfer. We're not creating or losing energy. The energy that we put in stays there, but it kind of moves. And this is one of the things which we can understand, that if the pendulums can swing at exactly the same frequency, if they have the same cycle of 2 and 4, forward and backwards, that energy can move. And we can see the chain at the top. One pulls the chain drives the other pendulum. So that's what we've seen on a number of other demonstrations. I have a number of questions about this. That explanation about why coupled pendulums work the way they do is great. It's not wrong. But it kind of leads me, every time I get an answer, I always look for the next question. So for me, the next question in this, one of the next questions, is why don't we just have an equal sharing of the energy? Why does one stop? Why does it keep going? And then how does it know? How does it know to come back? How's that happening? What's making that happen? And so that's one of the questions I'm still puzzling through. So you have a think about it. You come back and share your thoughts. The bigger question that I'd kind of like you to think about, because you've seen this before, is what do you think will happen? This is kind of my big question for tonight. What do you think would happen if I, rather than starting one still and the other one swinging, because we've seen that, what do you think will happen if I start the pendulums, what we call out of phase, swinging in opposite directions, if I let them go at the same time? So what do you think will be the result of that experiment? Will they just keep swinging? Well, because we've kind of got opposite energies. We can think of it as opposite energies. Will they just cancel out, stop swinging, or they'll do something else? So have a think about that. Start feeding in your answers. I'll give you a little bit of time. I've got another activity to go and share with you. So think about that particular question. We're going to change cameras again. And this time we'll come back. We'll get rid of the driven pendulum here. And I'll bring in another pendulum. This one's a little different, apart from dropping it and breaking it. So this is a lot heavier, and rather than being on a string, as in string theory, it's on a spring. And I've spent a bit of time adjusting the weight and the lengths of all of these things so that the cycle, the period of the bottle going up and down, so that cycle is pretty much the same as the cycle of the pendulum if I swing it side to side. So just like our coupled pendulums, where they need to be exactly the same length, so they have the same cycle time, the same frequency, I've adjusted this experiment. So this cycle is almost exactly the same as this cycle. And when you get cycles close to each other, interesting things can happen. So let's have a look at what interesting things can happen with this. So let me first start by having the bob, the weight, the bottle here, just go up and down. Seems to be behaving quite nicely, just like a good, oh dear, hang on. Oh, now it's swinging. Oh, no, hang on. No, it's gone back to up and down. All right, that's good. That's, well, hang on. No, it's now a pendulum. All right, that's, well, hang on. It's gone back to a bob. All right, so I started it as a bob, so it should probably stay a bob. Except now it's a pendulum again. So I started that off oscillating, cycling up and down. And we can see sometimes it did this and then it transitioned to a pendulum and then back. And it kept cycling between the two. Same thing happens if I started as a pendulum. We can see now it's bobbing. And after a few bobs, it'll then be a pendulum and then back to a bob. And our natural systems on the planet are often involved not with one cycle but many cycles, and those cycles are very, very complex. When they start interacting, we can get all sorts of very elaborate and apparently chaotic behavior, which is really just emerging from these kind of interacting cycles, just like that pendulum bob. Let's go back. We've got time, I think, to go back and have a look and see what kind of answers you've got from that other experiment with the two bobs, if you can remember those. Just as before, B, I'm not even sure what B was. I can't remember that far back in history. All right, so we'll start them out of phase. 3, 2, 1. And there they go. And there they keep going. And there they keep going. And at any moment now, they will just keep going. But then all of a sudden, they just keep going. And they don't behave chaotically at all. And that just poses to me even more questions. Even more questions. Keep thinking about how you might explain any of what you're seeing there. Now, I'm going to stop that because I would really like to show you just another couple of really quick activities which are kind of related to cycles, just like our pendulums. I'll take our pendulums out of the way. And I'm sure at some stage, all of us have probably dropped a dinner plate on the table badly, and it's kind of rattled and spun around. We've all heard that noise at some unfortunate point in our life. It's better than the sounds of things breaking, perhaps, but we've all heard that kind of rattling sound as a circular object is kind of cycling, spinning around. What I have now to finish on is just a quick question. Here is a tube. We'll probably zoom in just a little. Mechanical zoom. There we go. Now, I can get this to spin, because we're into cycles, so we should get it to spin, by kind of flipping down on one end. that will get this to start rolling backwards, but it'll also push the top away. So this is spinning this way, this is spinning that way. So it'll start, in fact, rolling around like this. You can see that happening. All right, we'll try that again. Bit more energy. All right. Now, the thing which you'll see in a moment is not because of anything stroboscopic, because of the shutters in the camera. Let me just put a big plus at one end. This looks a little bit like a battery to me. And we'll put a minus. We'll put a minus at the other end. There we go. All right, so a plus and a minus. That should be reasonably visible there. Now, I'm just going to do that again. So I'm going to push down on the minus end, the negative end, and just have a close look and see what you see. Just going to bring that back into somewhere where you can see it on the minus end. You might or might not be able to see that on the camera. We'll try one more time. Try one more. Let's see whether or not you're seeing on the screen what I'm seeing here. That would have been good. One last one. Is if you're looking carefully, what you will see, and try this at home, piece of tube, make the length three times the diameter of there, and what you will see if you flick down on the negative end there, is you will see the negative 3 times in that rotating mess, but you'll never see the positive. If you flick down on the positive, you'll see the positive 3 times, but you'll never see the negative. So have a think about why that might be the case. I'll leave that as my last question for you tonight, and I'll be interested to see what ideas you've got or any additional questions. So thanks for your attention and happy thinking.
Thank you very much, Stuart, for providing us with a lot of questions and also a little bit of comic energy there. So thank you very much. And I want to ask if we have a question from audience. We do have one. And the question is, were the pendulum swinging in sync intentional?
So it's not a case of intentional. It depends which one you're meaning. With the original activity of coupled pendulums, it's not a case of intentional. If you make them the same length, start one swinging, they're going to start working as you saw. So that's just how the phenomena works, and that's one of the things which is interesting.
Mm-hmm, mm-hmm. Also, I noticed that during your last experiment or demonstration, the plastic tube, when it was spinning, looks like it was bent. So there's another question for us to think about.
Sure. The slight bending, that is an effect of the shutter in the camera system because they scroll down. So what you would normally see, try that at home for yourself, is depending which end you start, you'll see one of those markings, the other one you won't see at all. And that's kind of the question. Why is that happening? And it links back into cycles and what we saw with the pendulums. There's a hint.
So, yeah, we can definitely see some answers in the comments. If anyone has any ideas, let's put them in the comments. And If there are no questions from audience for now, we will get to them during our discussion session. So thank you, Stuart, again for now, and we will see you soon during the discussion session.
See you later.
And back at the studio, as you can see, not only new equipment just came up to existence, also more importantly, Adam.
Hello.
So welcome back. And Adam, we know that you are very active in initiatives that want to make educational curricula better in Czech Republic. And I don't know what you were expecting when I started that sentence, but I wanted to ask you, how does it go? Do you feel like pupils in Czech Republic have a better experience with science education now that as they had, like, as we were mentioning, 30 years ago? And what are experiences with it?
I think it's better and better because a lot of teachers want to learn new things and they want to learn with technologies and stuff. So this goes better and better, I think. Because maybe it's because I know only the active teachers. Most of them, most of the teachers I know the active ones, but I believe it's better and better.
Okay, thank you. And also, as promised, everyone will get the same question, and it is, do you recall an experience from your childhood that inspired you to do science?
Yeah, I don't think that I have like exact moment or some interesting story, but I could remember that my father bought me on Christmas some science kit with experiments, and I got one experience with me from the box, and it's just magnets on the stick, and it was nice thing. Yeah. Okay.
So it was a toy this time?
It was a toy, yeah. So, and it was like full box of experiments, so it was quite nice. And this is one of them.
It's beautiful that we saw in a lot of cases that it was teachers that inspired people to learn more about science, but also it could be toys or natural phenomena that make you curious about how things work.
Yeah.
And with that, again, I would like to leave the physical stage to you, so you can do your experiments.
Yeah.
So,
Thank you.
Hello again. So we are going to talk about circadian rhythm, which is not like physics topics, but it's biology, but I add a little bit of physics on this topic. And circadian rhythm is quite important cycle in our bodies. It is on our inner clock. And we can look on it just in the beginning. And here is our circadian rhythm, yeah, from the beginning, from the like midnight to the midnight, yeah, because it's a cycle, yeah, so it goes from midnight to midnight, and there is a whole day in the middle. And we can see some changes happening in our bodies, like our hormone levels are changing. For example, the cortisol level, it's like highest here, yeah. In the evening, is it in the evening? Yeah, it is in, no. I'm just a little bit confused. No, it's in the morning, yeah. In the morning, and the melatonin level, which is also really interesting hormone, its highest level is during the night, because melatonin is responsible for a good sleep and other processes in our body. And I told in the beginning, on the start of our stream, that we are going to talk about circadian rhythm and light. And I also have a question about the light, and which is, okay, what color of light affects our circadian rhythm the most? Red, green, blue, or UV? Yeah, just think about it a little bit and type it down. What you think is the color what affects our circadian rhythm? Because there is such a color. And we can talk how our circadian rhythm is working in our bodies and how melatonin is produced in our bodies, because that's the most important, interesting thing in this topic. And we start with our eyes. Yeah, this is just some funny eye, yeah, jumping, but don't try this at home with your eye. Yeah, it's not a good idea. So we just look for a brief moment again to our circadian rhythm. This is the expand picture of it, because every time in our rhythm is good for another activities, like for physical activities, for a good sleep, for digestion. And this works because this was evolved by evolution for hundreds and thousands and millions of years to have this rhythm in our bodies. And everything changes because of electric light. Because electric light a little bit destroyed our circadian rhythm, and it is destroying our circadian rhythm even now because of the artificial lighting, which is everywhere, even in your houses, and even the screen which you are looking at, destroying your circadian rhythm. Nice. But don't turn off our stream. Stay here, because we can talk about a little bit more in the minute. So we start with our eyes, because in our eyes there are a lot of receptors for light, and there's like 5 types of receptors. Probably you know 2 of them, the cones and rods. But the cones and rods are not really important for producing of melatonin, not that much. The cones are responsible for the colors, yeah, and the rods are responsible for the lightning level. That's the most important thing. But there is also the 5th sensor, which is called melanopsin, and this melanopsin is responsible for the melatonin production. Because, yeah, you see now the pictures of the all our receptors. And I think this is the time when we can look at your answers right now. And it's here, C, RGB, it was blue, okay, blue. It was a D, UV, okay. And there's blue, also, okay, D. And UV is also D. Blue. We have a lot of blue life. Nice. Well, it's positive and negative affecting. Oh, that's nice. Positively red, if negatively blue. I think it's blue. Or I don't know what's that. Blue, yeah. This is the fixing. Okay, we can look at it. This is our lights. Yeah, these sticks are our lights. Yeah, this is red, blue. This is UV because I don't have UV color, and green. And we can like simulate the melanopsin response or the struct of information which melanopsin gives to our brains with the balloons. Yeah. And yeah. So this is like a struct of red light to our retina, to our melanopsin, and nothing really happens. So it's not red, but nobody types red, so don't care about that one. And we can try UV light, and UV light, okay, we tried it. Yeah, it's not really responding, nothing really happens. So not that one. And we can try also the green, because nobody typed green. So we try it first. Okay, so that happens. And all right, that's interesting. And we can try another stick. Yeah. We can try the blue stick, also the blue light. This is blue light, and we can see what happens now. Yeah, it was also the shock of information to our brain, and now our brain is stopping to produce melatonin. Because if this information comes to our brain from our eyes, melatonin is stopped producing. So it is blue and green. And we can saw it also on this graph a little bit, because this is the sensitivity on every sensor in our eyes, the sensitivity range of different colors on a spectrum. So you can see that like the alcones are really on the, yeah, I got that. It's moved a little bit, I see now. It's not that good. But the melatonin is really on a top sensitivity, it's on a cyan color, on the little bit bluish, greenish color, and also on the colors like surrounding this cyan. So it's also reacting on a blue and also on a green. So if we want to have more melatonin in our bodies, we need to avoid these colors, these lights, like the bluish, greenish, and all between, all in the middle, all in the middle colors. And we can do it to have a good lighting, for example, before we go to bed. That's important. Because melatonin is responsible not only for a good sleep quality, but also it is a good antioxidant. It helps to clean our bodies from all the bad stuff and the famous word toxins. But I don't like that word much. And it's good also for our mental health, because if you sleep well, you can be more optimistic, and that's a good thing. And it could regulate the body weight also. There are studies for that. And there's also studies that melatonin level, the low melatonin level correlates with a high level risk of cancer cases. So that's also a good thing to have it in mind. But now what we can do with that? We can use better lighting, and now maybe I could ask you what lighting do you use right now? Do you use like regular light bulb or the fluorescent lights or the LEDs, which are quite the most famous one nowadays? So what do you use? This LED, regular light bulb, or the fluorescent light? What do you have in your room now? And if we're gonna look in nature, which spectrum, which lighting we are using for 100 years, we can see that for a sun, it's like the full spectrum during the day. It's from the purple color to red. From the evening, the blue wavelengths are decreasing, and there is more on a red part of the spectrum. And during the night, our ancestors used fire, because fire was like common source of the light. And there is almost or not that much blue color in the spectrum, but it depends what fire it is. But in general, fire from the wood, it has this kind of spectrum, or this is from the candle. And did have somebody write what type, what color, or what lightning is using, or not? Maybe not, because it wasn't really official question. So we can look to our lighting, and we need to dim lights a little bit. Okay, in the darkness, and we can. Oh, now it works. We can look on some spectrums. Yeah, this lighting is LED lighting, so it's LED bulb. And you can see now it should, yeah, this is the spectrum. And we can measure the light coming out of this bulb with our spectrometer. And if we measure it, we can see our spectrum. This is like good light bulb for work, you can say that. Because there is a lot of blue, so your melatonin level is not that high because of the light, so you can work under this light. It's good to have that. And if we're gonna use a different lighting, for example, the fluorescent light, it depends which type you used, but this has a cold light. And we measure it again. We can see something different, some spikes. That's strange. It's not like the one little hill, but it's like many sharp mountains. So it is a different spectrum. It's maybe better, maybe worse for something, but this spectrum has one bad thing, because you can't really know you don't recognize colors that well under this light, so it's not that good. But we can add another light bulb. Here is also phosphorescent light, and it's a little bit warmer. So you could think that there's almost no blue or no green. We can look on it, and there is the spike in this section, which is like responsible for melatonin stopping producing. So it's better for like evening, or if you go home from your work, you can use this lighting, but it's not ideal for evenings. But we have the special LED light, which is not here, which is here. And this LED light is nicely orange, and we can see that there is almost no blue. Yeah, almost. There's a little bit of cyan, that's a little bit bluish. There is a little bit of green, which is not ideal, like right before you are going to bed. But there is a lot of red colors, and it's good for evening. This is good evening lighting, good evening bulb. And we also used one type of light before our bed often, and that's our phone. Our phone also have some of the phones have LEDs inside. So if we check it out on our spectrometer, and we turn out the light, and yeah, you can see it now. Sorry. Yeah, you can see that there are like 3 spikes, because there are 3 LEDs, like blue LED, green LED, and red LED. And if you want to have a good sleep, you should avoid the mobile phone before you are going to bed. But there is a trick. Haha, clever minds find out that you can use the filter. The red filter you can set up in your settings on your phone, and then the spikes from blue and green just vanished, so you are remains just with a red color, and it looks like this. Oh, it's not good, but so this is like normal, and this is with the this is with a red filter. So it's good to use that for a good sleep. Or you can use better light, or you can use these goggles before you are going to sleep. That's also a possibility. But the best thing is just common sense and to be be in touch more with nature, and you just should just obey the sun and how the sun is shining. So the healthiest sleep is going sleep with the sun.
Thank you, Adam, very much for the demonstration. I really loved looking at the spikes, especially at the mobile phone, as you can see. Yeah, thank you very much. I'll take that. So
these are not that great, but this one's better.
No, but we match now.
Yeah.
That's great. Yeah. Okay, and I wanted to go to a question from our audience. So if we have one. So Tomasz actually asked, in reference to melatonin, blue streetlights are believed to be useful in preventing suicides and street crime. The red ones work opposite. Have you heard about this fact?
Not really. I know that in general the street lights are used for reduce the crime on the streets, but I don't know this because we usually use the sodium lamps on the streets, and there is not that much the blue part of the spectrum, so it's like healthier for only for you like human being, but also for insects, because insects are also. The Japanese conducted such research. Okay, I check it.
Okay,
nice.
So we'll have to
That's
check this one out. But I've heard that they help with prevention of road crashes and accidents with blue lights on the roads, because it helps drivers not to fall asleep when you use LED lights on the roads. And so it might help also with, for example, pedestrian crossings. So they make, or they pay more attention to the crossing when it is lit by a blue or more bluish light, which also have some side effects.
Yeah, that's the idea, but it completely destroys your rhythm, like your inner clock.
Yeah, you should be.
So it's not that.
Yeah, you shouldn't be driving at night in the first place.
Yeah,
right? You should
sleep. You should sleep during the night. Yeah.
Right. And I would like to also ask you if you know how consistent is the circadian rhythm, for example, across different cultures or different like regions. Is it universal for us as people, as a species, or does it vary based on where do people actually live for 100 years?
Yeah, it's really based on how developed is your country, because here in Europe we have a lot of artificial lighting in the streets and in our homes, and our circadian rhythm is not that a rhythm, it's more a chaotic system in our bodies. But in a forest area or less industrialized area, you can find that the rhythm is more like the rhythm, like regular, and everything is fine. But nowadays, because of the artificial lighting, we are destroying our rhythm, and that's kind of, this could be dangerous for the human.
Okay, so thanks for bringing this cycle up, and this was our last demonstration. And now we will move on to our discussion session. And I like these glasses and how they look on me. So maybe I will keep them.
No.
Okay. But we can't hear you right now, so we will have a short time frame for figuring our issues out. So it's not right. We just figured it out. And I think the sound is coming through. And we will test it. So if you can all hear us, I want to start with circling back to the start. As we mentioned, we will ask you, or the audience, the same question as we asked you, our performers, and it was if there was a kind of experience for you, what was it? What was the story? And I believe we have one more answer from our audience, so I would like to bring that up. Not only sound is a little bit lagged, but also our answers, but we will get them up right here. And so we have a story of experimenting with peroxide and a random mushroom. I'm not sure what kind of mushroom that was, and in an old laboratory glass when I was a child, and it was so exciting. So another kind of experiment that can excite and encourage you to do different stuff and to ask questions how things work. And now I would like to keep with the theme of cycle. And my first question in this discussion session would go to Stuart. Let me give a little bit of context. We started with a theme cycle that we want to reflect on a cycle of personal development of a science communicator. And I did not say too much about it, but what we were thinking was that you usually, as we saw, science enthusiasts get inspired during school by the teachers or parents or someone close to them. And then they go through their own personal development where they discover different things. They want to be storm chasers. They want to know more about physics, more about biology, all other things. And then they get to a point when they are the ones that inspire others in their journey. And so they circle back to the point when they were inspired, but now they're on the other side. And my question to you, Stuart, would be that I'm not saying that like you are the most experienced in this part of the cycle.
The oldest, yes. That's what
you joke about it much better than I do. So I will leave it up to you. But my question is that you, as a science nomad, yeah, I have this thumbs up. I don't know where it came from. You, as a science nomad, do performances or instances maybe do not have English as a first language or second language. Do not they speak it as fluently? And I wanted to ask you about how were you developing your own like universal language where you can inspire others in science without using a lot of like natural English language or something?
Yeah, great question. I will probably struggle to see how I can answer that in a brief answer. Certainly, during the trajectory of my life, I've been curious all the time. That's led me to seek assistance and fuel my own learning. So I've always been a lifelong learner. Others have helped me, school. And when I got to university, that also gave me the opportunity to work with science communication, working with our science centre, our community science centre, which then grew to a national science centre. And that science centre, Questacon, meant we were able to train probably 400, 500 science communicators that are now available. Since I kind of retired, that's allowed me to go and work around the world, mostly in emerging countries. And the thing which is really coming to your point about the language, by working with hand activities and my particular passion, which is fostering thinking, I'm not trying to give answers. And giving answers and teaching, not teaching, but teaching is a very challenging activity. But fostering curiosity, getting people to think, you don't need a lot of language for that to happen. And so that's really been my recipe. I'm not interested in giving you an answer. I want to give you questions. And if you keep asking questions, you're going to keep learning. Whether it's science or not so important, but keep learning. And so that's really been my recipe for how I've lived and how I work with other people.
Yeah, thank you very much. Yeah, what I take from it is that you can inspire curiosity just by showing things, don't need that language. And I just think about the rainbow. You just see the rainbow and it inspires you to be curious about how is it possible. And I wanted to go to questions from our audience. So we have some. And a question from Lucia is, what do you like the most on teaching chemistry? And I think this is for Mark. Mark, we can't hear you right now. Could you unmute yourself, please?
Yeah. Okay. Now you can hear me?
Yes, thank you.
Okay, thank you. It's more or less the same answer as given before. It's very nice to make children enthusiastic about chemistry by teaching them things, but the most important thing is to get them ask questions, and then they learn. So I completely agree with the previous speaker. Yes. Okay.
Thank you, Mark. And now I would like to ask Anja. Or, yeah, we have a question for Anja, but I will go first. Anja, you wanted always to be a storm chaser as a child. And yeah, you did not end up being a storm chaser, but you're on a team of exotic particle chasers. So I think that worked out pretty well for you. And also, I wanted to ask you about CERN and going in the phase of the cycle of personal development. I wanted to ask you about if there is some kind of inter-department education, for example, in between people at CERN working in different departments, working on different things. How does it go in CERN?
So yeah, CERN is basically all about collaboration. So we're really working all together for, achieving the four main pillars, one of which is, in fact, education. So it's not that surprising that just last year in October, we've opened this new outreach center called Science Gateway, which is where I'm at now, although I am in a not so fancy storage room. with my coat in the back for some reason. So yes, education and communication of science are really, really important at CERN, and I'm really happy that everyone seems to be working towards enabling the public to learn more about these, as you said, exotic particles.
Thank you, Anja. And now a question for Tomek. What I love about your setup is that you give us a lot of opportunities to ask you questions. And my first one would be, have I seen some awards on your shelf behind you? What are they? Are the glass ones? They look like awards. Yeah. Maybe Tomek froze. No, he's just joking.
Which one? Which one of the awards you want
Let's
to
take the
see?
blue one. Blue one. We were talking about blue lights, so let's take the blue
Blue one? Oh, this is the first one I ever got. So this is the Northern Science Center Verbund Award for Outstanding Performance in 2015 in Estonia. A very nice festival, a very nice event made by AHA, the Science Center from Tartu, Estonia.
Yeah, I love that your rubber ducks have the same prominent place on your shelf as your awards for best performance.
They do. Not all of them, some of them.
Some of them. We have a question from our audience, so I'll go back to them. And back to Anja. Do you have any special resource or special things for experiments like old TVs, etc.? A special resource of special things. Yeah, do you have a storage full of things like old TVs that you can do experiments with?
Unfortunately not. Even this TV took me forever to get. It was really funny how when I came to CERN 6 years ago, there seemed to be these TVs and screens everywhere. But then 4 years later, when I was trying to get one, everyone was just like, oh yeah, we threw it away. So it took me 2 years to get this little TV for the show's own personal collection. So we are keeping this one as safe as humanly possible.
Yeah, what I loved about the TV was that we saw an illusion of a distorted face in 2 different ways. One with optical illusion from Tomek, and the second one by magnets from you. So it was a nice touch on what kind of illusions we can get with faces. And I want to go to David this time. And there's one cycle that we did not talk about, but I really like, and that is hype cycle. There's just one company that do these hype cycles, and what they do is they rank technologies on a scale of their development or cycle of their development. The first thing is emerging. So this is new research, emerging technology, and we just get to know it. Then it's the peak, that's the hype. There are a lot of investors want to invest in this technology. And then there's a valley named trough of disillusionment when the technology does not deliver on its promises, and then it gets back to something that is useful. So this is something that people discover that technologies usually go through. We know that you are a biotechnology engineer, and in biotechnology it could be the hype now could be mRNA vaccines. The disillusionment could be in biofuels, for example, and the usefulness, plateau of usefulness, as it's called, maybe, for example, genome sequencing. And I wanted to ask you, do you know any, or maybe work with any technologies that will be in this first phase of the cycle, which is emerging technologies that we will only hear about in the near future?
I don't know if I'm working with such a technology, but I studied about such a technology, and it is genetical engineering of organisms, so we can use them in factories producing goods which are like safer for the environment and cheaper to get, we're closing to getting these products safer for the environment, but we are far away from the price. It's still too expensive to use this technology, and I think in recent years it will come that they will start to get cheaper and cheaper and affordable. So we will use this technology, and then the legislation is like really tight in Europe. So it's really hard to use genetically modified organisms in like large scales. So,
So if you want to watch out for biotechnology, a breakthrough, one of the candidates for the next one could be genetically modified organisms. Thank you, David. And before we move to another question from our audience, I would like to ask Adam, which took my glasses, or his glasses, which I thought they're mine. And I wanted to first congratulate you on a very tangible demonstration with the blue rod and the black balloon. It really woke us up, maybe not really a very uncomfortable way, but it was tangible. And I wanted to go to LEDs, and we've heard, or maybe there is a very interesting story about how the blue LED was discovered.
Oh, yeah.
Have you heard about the story?
Yeah, I heard about it. And I saw the video from Veritas Serum, direct from Veritas Serum. That's amazing. The whole story about that, and that's nice. And even it's interesting to realize that every blue LED, every white LED is in basic the blue LED. That's interesting thing, I think, because nobody thought that, but it's like interesting.
Okay, so a tip for a very interesting science story is a story about the blue LED. And now I want to get to the question from our audience. Okay, I use a lamp with 10,000 lux light. Okay, in the winter for hour, at the mornings, like cure for depression. Okay, so this is the topic that Adam covered. So circling back to it. And have you heard about these kind of medical usage of strong light in the morning?
Yeah, I heard that like that light is used for like a cure for various disease like depressions and also for some skin disease, but some of them are not really like scientifically proven. But this depression thing, we know that if you don't have enough light during the day, you can feel depressed. You can feel depression, and you can like you can gain the disease of depression. And the easiest thing to do is just going to outside during the day. Don't stay inside, indoors, and that's basically it. But it depends in which which part of the earth do you live? Because if you live like in Finland on north, you need, or it's better to have additional lighting during the day. Because you don't have enough light during the winters, because the night during the winters are longer, especially in northern areas. It's like more longer than in the Czech Republic, for example.
Yeah, or very southern, as we have. As we said here, you can go too much north or too much south.
Well, I think that Australia is not that southern. It's like
not Australia, but Antarctica is close to Australia, so definitely closer to Australia than to us. And okay, thank you very much. And we have another question from our audience. Anna is asking, I would like to ask Anja if there is anything specific she would like to achieve. So your future plans, Anja?
My future plans currently involve a big question mark, because I am finishing my contract at CERN end of this year. So I'm in the process of finding my next step as we speak. So yeah, I think on the other hand, I have achieved quite a lot this year. So I think I need to reset my goals at the moment, because just 2 weeks ago, I performed at the Edinburgh Science Festival, and it was absolutely my highlight of the last few years, I would say.
Perfect. And I think we have one treat for you. And that is a video of Mark's daughter that we saw a short or a screenshot of, but I would like to get back to, because we saw a lot of cycles, and one of them was, for example, circadian rhythm that is somewhat biological, or it is biological on a large scale, but there is one biological cycle that we did not get to, but Mark's daughter is very neatly showing us, all of us, so we would like to see it in the video.
This is my science YouTube channel. As you all know, plants need water and carbon dioxide and light. The plant uses carbon dioxide and water and light to make glucose and oxygen. This process is called photosynthesis. At night there's no light, so there's no photosynthesis. To stay alive, the plant burns glucose. The plant uses oxygen to burn glucose. Action products are carbon dioxide and water. Here you can see the chemical formulas. If you look closely, you can see that this carbon is used to build glucose. And this glucose burned, carbon atoms used to make carbon dioxide. Carbon is in a cycle. So the question is, can we make energy from glucose? Here we have potassium chlorate. When it's heated, it decomposes into oxygen. Oxygen from potassium chlorate used to burn sugar. I mix potassium chlorate and sugar. And now we make a good mixture. Let's slice the mixture. It works!
And our thanks go to Mark for providing us with this clip that we could get a peek onto her YouTube channel. And so, Mark, quick question: how much help did she need from you to make this video? And Mark, you're muted again.
Yeah, I was muted again. The fun thing is, we make a program to make this movie, and then we start, and then suddenly she says, "Stop! I do not understand it anymore." And then I explain the whole situation to her, and then she says, "Okay, we're going to start all over again, but now I'm taking lead." And this is what happened, and this is the result.
Perfect. Thank you very much. And I think it really nicely manifests the cycle that we were trying to reflect on, the cycle of the development of the science communicator. Maybe we saw the first phase of the cycle right there. And as we are nearing, what is it? Almost 10 p.m. our time. And we just learned more about our rhythms. We should probably be going to the finish line. And I wanted to close this session with one question for everyone, and that is regarding next few months. We will have summer. Summer is full of festivals, some of them science festivals, events. So I'd like to ask you if you have any more tips on interesting events that we should not miss, or that you are just looking forward to attending. So maybe I would like to ask Stuart first.
That's Ljubljana and Znanstvál. Do yourself a favor. Best big little science center in Europe. So fantastic festival. Get there.
Thank you. So these are two invitations to Znanstvál. Something good must be there. So maybe this time I will have an opportunity to go there, as I always wanted. Adam, do you have any recommendations or tips on invitations for us?
Yeah, I was also thinking about Znanstvál, but I'm going to also be on a science festival, Science on Stage. So it will be in Turku in Finland this year in August. So that's a tip from me.
Mm-hmm. David?
Yeah, for me, it's I'm looking forward to Znanstvál. I'm looking forward, and I'm happy to finally go there after like 5 years of wishing to. So
yeah, Ljubljana seems to be the most influential European city in our bubble of science enthusiasts. And Mark, do you have any other events that we can keep an eye on?
I hope to organize my own event in this school next school year. So please come and join us.
Okay, if we can, we will. And Tomasz?
Already mentioned the Znanstvál, so I will go now with Science Picnic in Warsaw, 15th of June. You can see, for example, Pavel from Heweliusze Nauki on stage, but you will also see Anja on stage, so that's also promising. That's should be a nice event.
Thank you. And as we virtually lost Anja, we cannot hear recommendations from her. But if anyone misses her, they can see her at the Science Picnic in Warsaw. So thanks for the invitation. And I think this concludes our discussion session. I would like to thank all of our guests that they found their time to show us experiments to inspire us and to inspire other performers, other science educators in different approaches to communicating science. I would like to thank our audience that made this interactive stream possible and actually interactive. Thank you for all your comments, all your answers, all your interactions. And also I would like to thank our team of Science On that works hard here in the backstage. Such everything works and only a few lapses here and there. And there's only one thing that I would like to add, and that is invite you to other Science On streams. They, as you probably know, they are mostly in Czech every month, but every 6 months they are international with our dear international guests and with me hosting it. So hopefully see you all either in 1 month or 6 months, and finishing with a legendary Eurovision classic, Good Night Europe and Good Morning Australia.